Okay, so we're going to take care of some AM modulation aspects in today's lesson. All right, so that was pretty interesting. I wouldn't say experiment because things like that have been done before, but I find this interesting that that you had to just receive the instructions and go and figure things out with with some help and to understand what's going on with the amplitude modulation. So I'm just talking about the way we conducted our lab yesterday. All right, I kind of liked it. So what's the idea with frequency modulation? Oh, not frequency. I'm getting ahead of myself. Amplitude modulation. Why do we need to modulate? Well, if we are just going to have a microphone on one end of the transmission link connected to a mixing board, and that is connected to an amplifier, and that amplifier is connected to a loudspeaker, then we just have a signal transfer from one place to another, and the signal is being amplified, and it's contained within the wiring, or maybe some wireless channels with the new wireless microphones that are going around now. So we don't really need modulation. All right. So that's how the audio systems work. However, now with the new era of digital technology, even then we are using modulation. Because instead of having a snake cable, a snake cable is a cable that contains many cables inside that goes from, let's say, stage to the front of the house, and the front of the house is the where the sound booth is in the public. So sometimes it's anywhere from 100 to up to 200 feet sometimes. So those snakes in the audio, in the analog world, yes, the signal is not modulated at all. It's just a signal that goes in from the stage to the front of the house, being processed, and is being shot back to the stage, to the amplifiers, and is being amplified and so on. But in the new digital era, as I said, there is no analog snake anymore. There is Cat5e or Cat6 cable, and it contains all the channels that are being sent from all the microphones. So there's something that's called stage box at the stage, and it is it's a transmitter because it's a modulator and it's a transmitter. Does it transmit over the air? No, it transmits through the Ethernet cable, but Ethernet cable in Cat5e is just using two pairs, one for transmit, one for receive. Now Cat6 and up, it's using two pairs for transmit and two pairs for receive. So still, if there are 24 or 48 channels being transmitted from the stage, well, you have to modulate it to transmit that over the two pairs and receive things over the two pairs. So things are being modulated. That's not an AM modulation, it's a different type of modulation. But why do we need to modulate things? We need to modulate things so we can fit and try to fit things in over the the electromagnetic spectrum that we have to use, that we are able to use, and so you can transmit that over a distance. Now, when you're listening to your car stereo or car radio when you're driving to school or to work or just driving, you are listening to a signal that was first produced and it was modulated, and it was transmitted, and then it was received by the tuner on the radio, and it was demodulated. Well, first it was tuned to that carrier, and it was demodulated and processed into your speaker. Now, because the frequencies are all present in the air, so remember, this is the result of us using the broadband type of transmission. Broadband means all frequencies are present at the same time in the medium, which in this case is air. And remember, we have three types of mediums that are mostly we're going to use. It's the air, copper, and fiber. Air is the air, utilizes antennas to transmit and to receive. Fiber optics, fiber uses fiber optics to transmit signal. And copper is popularly known as copper, which is electric wiring. We're not going to distinguish that, okay, is this aluminum wire? Is it? No, it's considered all copper, just to simplify things, okay? So, that's why we need to modulate signals so we could utilize, for the most part, broadband type of transmission. So we could fit many radio or TV channels over the air, so somebody with a tuner can choose which station to tune into, and to utilize the signal that's coming through. It's for the efficiency. All right. So the main idea that we utilized yesterday and we were hovering around was, what do we have when we combine frequencies? Now remember this little multi-sim simulation that I showed you some time ago, that was with the differential amplifier, and trying to, the purpose of that was to eliminate the noise. So when I start simulating that, I'm going to pause it. So there you go. So you see over here we have, let's take a look at that, yellow channel 1 waveform. Right? What do we have? We have one type of frequency, which is the intelligence, and we have the noise. So we have a little bit of a hairy waveform combined with the noise. If you introduce two waveforms into one medium, those waveforms combine into something that is going to result into something else. In this case, it's the noise, so it's an undesirable mixing. Mixing is combining of the waveforms that occupy one medium. Now, so what happens is we get the combination of those two waveforms, and this is an undesirable effect. Okay, I'm just going to I should stop the simulation so it doesn't occupy my microprocessor thing. All right. So what happens if we combine two waveforms in a little bit different way, because we can still use the phenomenon called as mixing. What are we going to have? If we combine one, that's the FFT type of timer we're using. So we're going to end up with the frequency, we're going to call it the carrier frequency. And let's say, so we have the frequency, that's a carrier frequency, and we're going to frequency intelligence. And let's say this one is 100 kilohertz, and this one is 1 kilohertz. So we're going to have that carrier here, which is the 100 kilohertz. I'm not going to put the units because mouse is, we know this is that one. So there's the carrier. And then we're going to end up with the carrier plus frequency plus the intelligence. So it's going to be somewhere here. And that's going to be 101 kilohertz. And we're going to, so this is the carrier plus intelligence frequencies. And we also are going to end up with the carrier minus the intelligence, so that's going to be 99 kilohertz. Okay. There is one more frequency that we're going to have present, because we have to have all the elements present, right? Right. Well, we kind of have tendencies to forget that, because that's also, we're going to see that 1 kilohertz here. But on our FFT function, on our oscilloscopes, we just saw this part, because this here is somewhere off the screen, right here. And that's the 1 kilohertz. It's still there, it's just that our FFT function on the scope was not applying, not displaying. So when we combine two frequencies, we get 4 things. For the most part, we get 4 things for sure. We get the one of the frequencies, of course, to be present, and of course we're going to get the other frequency because it's there, and we're going to have the sum of them, we're going to have the difference of them. For the most part. But as a result of all this mixing, in reality, we are also going to see 2 more things. We're going to see noise present, and we're going to see harmonics of some of the frequencies. Now, just keep that in the back of your mind. You only saw this little spike here and little spike here. Why only this spike? Because the frequency that we're using to modulate was that really annoying 1 kilohertz. And that was a sine wave that we did. And you will be able to see just a spike here and maybe some harmonics, but they would be so insignificantly small. Now, what would happen if this intelligence signal was, for example, my voice? Would that still look like a spike on the screen? Now, that we're going to take care of next time we see each other in the lab. See what is going to, what is this thing going to look like? We're going to connect a microphone instead of the second generator, and we can speak to it and see what that FFT shows us as the side bands, because the sum of the frequencies is called upper side, and The difference of the frequencies is, we're calling it a lower sideband, upper sideband, lower sideband. And that all is being transmitted through the air or through some different mediums. It could be copper or fiber as well. Don't forget that. But when it comes to radio, we're mostly talking about transmission through the air. Those will not look, when we talk like when we talk with our voice or we play music through it, they will not look like that. And we are going to actually hear that in our little clock radios. But because of the power of the signal is so weak, and that's good because we don't want to get in trouble, we have to put that radio pretty much on top of the circuit in order to hear. But we are able to demonstrate that with the 1 kilohertz, and yes, some of us found that it was quite annoying to listen to that. I should probably show you some frequency or sound syntheses on how we can combine waveforms in order to get something that's more pleasant to our ears, human ears. All right, so as a recap of this, we get two frequencies combined, and we call that thing mixing. The two frequencies are mixed together. What do we end up with? We end up with those two frequencies that are mixed in, and we're going to end up with this sum of them and the difference of them. All right, for the most part. And don't forget, there will be noise and there will be some harmonics. Okay. Where are we here? There we go. And whoa. Yeah, there we go. Just going to, yeah, we're doing good. All right. How are we doing here? Good. So, amplitude modulation is the topic of today. We're going to get some ideas and possibly some preceding for some exercise that we're going to cover when we meet each other in person, which is going to be that Monday. All right, so modulation, amplitude modulation. Next, what if there are different types of modulations? This is just one type of modulation. Next time we're going to take care of a frequency modulation, which is also so much fun. I could actually, I was happy to see that you guys, you guys lit up when you saw some of the aspects of that, of what was happening. Modulation involves combining an information signal with much higher sine wave frequency of a constant amplitude. All right. So, here, where's my thing? There we go. Come on. Hi. There. All right, so what we have is we have a carrier. What this one is saying here. Modulation involves combining information signal with much higher sine wave, so information signal. And for the information, we also call it the intelligence signal. That was that 1 kilohertz waveform that we were introducing into the circuit. And we were mixing it or combining it with the higher frequency, which we called it a carrier. And that carrier was of a constant amplitude. So the carrier that is introduced is not changing in amplitude, and it's just, if I can draw it, it's constant, right? Constant, more or less, yeah. Here's my drawing skills. And we're introducing that intelligence signal on top of that. So a mixing is going to occur, right? So that's what this one is saying here. The interaction between the information signal and the carrier is called mixing. Amplitude modulation is one of the simplest forms of modulation and continues to be used for many applications as both generation and the detection do not require complex circuitry. So it's a simple thing. Now there's some trade-offs for that. With amplitude, for example, interference. AM, if you ever listen to AM radio, which is the amplitude modulation radio, if there is a storm nearby and there is this electric kind of lightning, you're going to hear that because it affects the amplitude of it's going to mix with the amplitude of the signal. So you're going to hear that. Amplitude modulation is one of the, okay. With amplitude modulation, we will be changing the value of the peak value, which is the value of the peak value is going to be changing because we're going to be changing the amplitude. So yes, and this is a formula for a sine wave. Here's the peak value, and here is the trigonometric version of the, here's the angular velocity, and the phase shift quite often is being used as 0, but here is the formula for a sine wave. All right. I just thought it would be okay to throw that in. Now, remember this here. Where is my, here it is. Remember that? We're combining two frequencies, and as a result, we're getting the frequency and the other frequency, but that's it. And then we're going to have the upper sideband and the lower sideband, right? Right. Double sideband. Full carrier, AM. Double sideband, full carrier receiver. Well, I'll tell you why. We are actually paying attention to whether we have the double side, or can we do something with it to save some space? That's coming up in the next couple of slides. There are several forms of amplitude modulation, but the most common is the double sideband full carrier amplitude modulation, where we actually transmit the carrier and the two sidebands, and they're being transmitted in the frequency division multiplication as a broadband through the air or through a cable, but usually through the air. And we're going to have a tuner that tunes to the carrier and how come I lost there we go. I lost some part of my screen here. So the transmitter and the tuner are, one is transmitting the full carrier double sideband, and the receiver is receiving double sideband, which is receiving the upper sideband and the lower sideband, and we only need to have one of the sidebands because the other sideband is almost like a mirror image of the first one. So why do we need to have both? Can we chop one of them off and save the space in the frequency spectrum so we could have more channels? Can we do that? Well, it's been done, and it's quite common thing to use if you don't need high fidelity kind of audio, for example. just for the voice, or from Morse code, which a lot of radio enthusiasts do use. AM is over a century old. Well, it's over 100 years old, and yet the basic principles can help us to understand the other forms of modulation, including digital modulation. So here's a philosophical statement. Crystal radios. Now that's a fun thing to do, and sometimes when you have nothing to do, when you're bored, or you're just excited about the topic, I would encourage you to make one of those. All you need is those earbuds. Just a regular earbud. See, like this one here? Can we see that? Yeah, just a regular earbud. It's a piezoelectric earbud, also known as a crystal earphone. It costs pretty much like pennies. Oh, okay, maybe. Oh, where the heck am I? Yeah, very cheap. And the cool thing about the whole thing is that it doesn't require power. So let's see here. There are several forms of, okay, so double-sided, okay. AM is over 100 years old. So, okay. Crystal radios were very popular at one time because it was a cool thing to do and it was cheap. As AM radios are still popular with the hobbyists, they do not require power. These crystal radios, not the AM receivers, because yes, the radio receivers do require power, but we're talking about something that's called a crystal radio because it uses the crystal earphone. Sounds kind of enticing because of the word crystal, and crystal earphone must be something high tech. Well, these are the piezoelectric earbuds, and you can research what piezoelectric is. So crystal radios were popular, and they do not need power. The crystal radios don't need power. They do not require a power source and were used extensively during the World War II to receive broadcasts. Well, World War II soldiers, you don't, on the front lines, you don't really have the luxury of finding some kind of a variety store to buy batteries for your receiver. So the crystal radio was perfect thing to have because it doesn't require power. Power from the actual carrier, because the carrier does carry a power. So just think about it. We are being bombarded with all kinds of frequencies. Our body is constantly being bombarded with frequencies that we are not able to detect, but we're still affected by it. It's all in the air, but just don't get too paranoid because it's fine. Trust me, I'm a doctor. I'm not actually, okay, but it's a funny thing to say. All right, so the power from the carrier is used to create audio voltage. So here's the antenna, and here is the one. Look, that looks like a tank circuit, right? You could have something that is called variable capacitor, and you can do that with that variable capacitor you can create with those empty rolls of toilet paper, or even better, from those paper towels, because those empty tubes are longer. You can wrap this thing with both of them, well, just one, and you can wrap it with coil, and then you can wrap it with tin foil, and you can move things around. So just if you want, just research on YouTube how to make a crystal radio, and there's a bunch of fun videos to watch. Most of them are short. On how to make a crystal radio. So here is the antenna. The antenna is picking up the energy that is in the air, and the tank circuit. You see, when we did the tank circuit for a transmitter, Remember when it was, whatever it was tuned to, it would shoot up the levels on the FFT screen. Well, the same thing goes the other way. If it's tuned to have a little, because you're talking milliwatts here. You're talking really, really small amount of wattage that the antenna is receiving, but it's still enough to create certain type of a voltage or electromagnetic variation within the antenna to create voltage that can be picked up by the tank circuit. And if the tank circuit, so that's why you need to have that tunable capacitor made out of those empty tubes from the toilet paper rolls or the paper towel rolls, in order to change the size of the capacitor. And by changing the size of the capacitor, you could tune this tank circuit to different frequencies, because the antenna is not picking just the frequency that you want to tune to. The antenna is being affected by everything that hits it, which means it's a broadband type of a situation. All frequencies are going to be present at the antenna. And we use the tank circuit to tune into a specific one that we want to tune to. And here's a diode to eliminate one of the sidebands, because we don't need both sidebands, because the same intelligence is being carried over both sidebands. And this energy that is being provided here into the tank circuit, and it's because it's simple circuit here, look, it doesn't need any power, because that energy is being used to power that little earbud, piezoelectric crystal, also known as earphone. And you stick it in your ear, because it's made, this thing, it's called earbud, so it's meant to go in your ear. You are going to actually hear some AM radio stations. So try that. Right, double sideband full carrier, AM transmitter, double sideband full carrier. Okay, there you go. Here's the acronym. A mixer circuit with two sources. The carrier and the intelligence signal is passed through, and it looks like a story. Passed through a nonlinear device, can produce AM signal at the carrier frequency, a mixer circuit. So here is, of course, we're using the transistor here to mix things, or to, well, as an amplifier. A diode or a transistor are nonlinear devices, also produce signal gain. Why do we need a nonlinear device as a diode? It's just to eliminate one of the sidebands. Because we don't need to listen to both of them, because they carry the whole same information. Plus, if they're going to be 180 degrees, because if you look at the envelope that we had produced by combining those two frequencies, you are going to notice that those two, upper sideband and lower sideband, are out of phase, 180 degrees. So you combine them and put them into some sort of a device, you will hear nothing, because they will cancel each other out. So we need to cut things out, cut one of them up. Okay, a diode and transistor are nonlinear devices, but we are using the linear area here in order to transmit that, or receive, actually. In this case, we are using a transmission here. And remember we had the two generators plugged into different sides of the potentiometer, variable resistor, and the position of the wiper would set the proportions between one and the other. That potentiometer is the simplest mixer. Now we can also do this. We could connect those two sources, except we have to make sure that the grounds are not going to create any conflict. So we can connect those two sources in series and just adjust the levels on one and the other, and that's the simplest way of doing things. So if you see something like that, or if you see that thing with the wiper, that's fine. You're probably going to see the potentiometer with the wiper more often than not, because the grounds are the same on both outputs, and if you connect them like this, then you're going to have that part grounded. So that's why the potentiometer with the wiper is the more common thing to do. So here's the E carrier and the E intelligence can be combined and shown as the resistive network like that here. And here is the tank circuit, which pretty much acts as, and get used to this terminology, acts as a tuner, because by setting up the resonant frequency of the tank circuit, we can tune to whatever frequency we want in order to transmit the carrier or receive a carrier. And then that means we can create multiple stations with multiple carriers, and each of the carrier can have intelligence that is the same. Human voice, music, radio stations. That's the idea. All right, intermediate frequency amplifiers. All right. On the previous slide, the output of an actual modulated carrier. Okay. On the other side, the output is on an actual modulated carrier. Okay. In practice, it can be difficult to design modulators and filtering at the high frequencies, so something that's called intermediate frequency is used. Again, let's read this. Let's go back to this. In practice, it can be difficult to design modulators and filtering at high frequencies. Why? Because higher frequencies are closer to noise. And that's one thing. The other thing is higher frequencies have less energy. So the equipment has to be really, really well. It has to be, if it comes to a receiver, it has to discriminate really well between the noise and the intelligence, and if the noise is compared with the or carrier, for example, then it is more difficult to accomplish that. The higher the frequency. So something that's called an intermediate. That's another interesting phenomenon, not phenomenon, concept that's being used. And I can hear a blue jay in the background screaming its head off. That means it's going to rain. There you go. So here's your weather channel. The same approach is used for receivers during the demodulation. What do we have? Here the blue jay. Here is the intelligence. Here's the speech amplifier, which basically is an audio amplifier. Here's the audio processor and whatever, So here is some sort of well-prepared audio signal that's going here. And over here, at the same time, we have an oscillator. And what does the oscillator produce? That oscillator produces a high-frequency carrier, onto which we're going to superimpose or mix the intelligence signal, and they all come to that modulator, which we just made yesterday in our lab. then it just being processed further and transmitted. And it goes out to the air. And that would be one radio station channel. What would determine what channel it is? Is it the speech? No, because that's speech. This here, this oscillator here, and the circuitry associated with it, but they will be tuned to the oscillator frequency. This determines what channel or what station it is. So, well, we're getting to the intermediate frequency thing here. I wonder if it's explained here. The same approach is used for receivers. Okay, so intermediate frequency. Okay, so the most common intermediate frequency is about 455 kilohertz, and they're also 10.7 megahertz. Yeah, but for AM, you're going to have that 455, which is 455 kilohertz is below. That is below the AM scale on your radio. So your radio can't receive that. But the intermediate frequency, the idea of the intermediate frequency is that let me bring up a screen here. Always get that. Seven by 5. That's what I want. There we go. Oh, here is a box that is going to receive things. And here is a box that is going to process things, and it's going to pass a process signal for further processing and output. And here is the middle stage. Intermediate frequency, IF. This here receiver receives, or it has a tuner that can be tuned to any frequency that's coming in from the air. But these are high frequencies. Now, if you take that high frequency carrier and translate that carrier into another carrier that is lower, you only need to have one good processing and amplification system that is tuned to the intermediate frequency in order to process the signal properly further down. You don't need to have this amplifier to be able to handle all the high frequencies here that are coming and hitting it, because whatever comes in or whatever station is being translated, the carrier is being changed from whatever it is to the 455 kilohertz, and from that the carrier is nicely stripped away. How is them used? Remember we did the frequency multiplier? It has something to do with that in order to accomplish the intermediate frequency. Why would we call it the intermediate frequency? It's because it is between the receiving frequency and the rest of so it's the intermediate type of situation that we have here. So somebody called it intermediate frequency. It still has a carrier, but the carrier is 455. By using the frequency multipliers and dividers, that IF is being accomplished, and that is then the carrier is easily stripped and discriminated by this intermediate frequency amplifier here. The carrier is stripped, only the intelligence is kept, and the intelligence can be used. So IF, intermediate frequency. And common, usually this would be for AM, this would be for FM. So for AM, 455 kilohertz, and if you look at the scale of, as I said, if you look at the scale of the AM clock radio that we have in the classroom, or if you even Google the AM scale, 455 is well below that scale. And that's where we want to have it. So it's not interfering with all the circuitry. It's not going to interfere with the tuning of the tuner of the other frequencies that are coming up, which means that the radiation of because two frequencies do radiate, those are not going to interfere with the amplifier that is supposed to discriminate those that carrier. All right, so in this block diagram, the oscillator would be a much lower frequency than the final carrier. Again, the much lower frequency than the final carrier. Okay, I'm just trying to make sense out of this thing here. It is what I explained here, right? Now, IF amplifiers in the circuitry normally have the sharp, okay, so I also explained what the IF idea is. So we could have very sharp bandpass filtered performance to ensure the modulated waveform only contains components of the desired frequencies. Okay, so just go back a few seconds and listen to the explanation that I just did. Double sideband. All right, remember when we were talking about the result, what's happening when we combine or mix two frequencies? We have the carrier, and see that the carrier is of the same amplitude, that doesn't change, and of course the amplitude of the carrier of the intelligence, of course, is going to change, because sometimes I'm going to speak louder and sometimes I'm going to speak quieter. So this would be the amplitude of the carrier, no, the amplitude of the intelligence, which is going to affect the modulated carrier when mixed. And of course, the frequency of my voice, I could speak loud, thinner voice, I could speak really thick. That frequency is going to change. And I remember when we were, with some of us, that I put the clock radio right beside our circuit, and we were able to regulate the intelligence frequency. We were able to change the tune of the tone. So that would be the frequency that is being sung. So it also has to have certain type of bandwidth in order to accomplish whatever we want to accomplish. And in this case, voice, because AM was mostly created for voice, and some, by the way, we can also do music through it. So some of the quality of the earlier radio stations were not as clear as the radio stations right now. Right? Okay. So in order to modulate a carrier with intelligent signal, we need to use a nonlinear device like a diode. The carrier and the intelligent signals are multiplied together, so the modulated carrier contains all the information in the... There's a mouthful here. Why do we need the diode? We need the diode to eliminate one of the sidebands. Because you see, we have two sidebands here. But the information, this information here, is all in one of the sidebands. So why do we need to occupy the bandwidth? We can fit more radio stations if we chop one of those things off, one of the sidebands. And that's exactly what's being done in some situations. Don't get the same quality of transmission, but sometimes you don't need the quality for just communicative type of a voice. There's a trade-off. You can fit more channels at the less quality, which you don't need when it's just transmitting voice annunciating type of a thing. Well, when you're talking about high fidelity music, you want to have as much bandwidth as possible, so then you're not going for those trade-offs as much. Still, there's some. Right. So in the figure below, we can see the AM waveform is being varied at the same frequency, intelligence. Well, I explained that already by using my thin and thick voice. The AM waveform below is what we would see in the time domain, and it is important to note that it no longer includes a low frequency component. In this figure we can see that the amount of modulation is different. This is something we can control. Yes, we can control the amount of modulation as a part of the design. Does it matter? Yes, it does matter. The modulation does. The amount of modulation does matter. Why? Because you want to have, when we are talking, we need to have as much dynamics as possible. What's dynamics? Well, the ability to distinguish between something that is loud and something that is a little bit quieter. Otherwise, it will be just one flat-lined type of a voice, which is sometimes desirable up to some point when it comes to some audio situations. Up to some point, but even then, that's by using the compression and limitation. So compressors and limiters are being applied to the voice or to the intelligence signal. But we still need some, because our human ears are not used to that one type of level. When I talk like this all the time, at a certain level, no changing, not applying dynamics, and not varying anything, it's becoming monotonous, and your brain is going to start ignoring it. And if you want to pay attention to what I'm saying, you're going to struggle with with staying awake. Excuse me. So that's why we do need to be able to modulate that. Now, by accomplishing the most amount of modulation, we are able to transmit the intelligence with certain dynamics. Now, of course, if it is a digital signal that is being transmitted, then who cares about the dynamics? But you still need some sort of dynamics in order to be able to distinguish the threshold levels of where is it that 0 ends and the 1 begins. So yes, you do need some sort of dynamics as well. Modulation index. If we continue to increase the modulation of the signal, long story short, modulation index, letter M, is the value of the intelligence over the value of the current, the carrier. Simple. And if you want to have that modulation index in percentage of modulation, remember in the lab we had to accomplish certain type of modulation, 50% modulation. Now, if you look at this formula and you remember what you've done in the lab last night, this formula looks much more colorful than if you had the theory first and try to remember the formula, and maybe you would forget the theory by the time you get to the labs. So that's why I say I kind of liked what happened yesterday. We get the lab first, and we really, well, not struggle, but we do engage in understanding what's happening. And then you get the theory to just show you what you have done. So yes, I did like it. So here is the modulation index. Remember, because we're going to be using that in other formulas. So the modulation index is basically how much the signal is being modulated. M is defined as the ratio of the time. It is expressed in the ratio no units, or sometimes percentages if you multiply it by 100. But percentage is not really a unit, it's a ratio still. And the most often is presented in percentage of percentage modulation. These formulas here, the formulas, note that the modulation index does not depend on the frequency of modulating signal, but it does depend on the voltage of the modulating signal. It doesn't. The modulation index doesn't depend on the frequency of the intelligence. The modulation index depends on the voltage of the modulation index, or the modulation, the intelligent modulating signal. If a modulating signal is voice, the amount of modulation will be dependent on the magnitude of the voltage created by the voice at any instant time. So we used 1 kilohertz, that annoying tone, and to our ears it is quite annoying, but to our eyes it's quite pleasing when looking at the oscilloscope screen, because we can actually see what is happening. Now when we're using voice or any type of a natural sound generator, such an instrument, trumpet, violin, or whatnot, then yes, it will be more pleasing to our ears. It's not going to be so annoying as the 1 kilohertz, but we wouldn't be able to analyze it properly while looking at the oscilloscope screen. And here is the amplitude modulation, the graphic analysis. Whoa, is this something that you have seen? Yes. Right. Now, I noticed that some of us did not struggle, but had a little bit of a nut to crack with the concept of excuse me, modulation amount. All right. So if you see just the carrier, straight, full carrier, and there is no bumps. It's just one straight carrier. So this part here, for example. And if it's all the way like that, Here is the carrier. The carrier is untouched, is unmodulated, which means the carrier, while it's unmodulated, untouched, so the percentage of the modulation would be 0. Now, when the more we affect the carrier, the more we modulate it. So if we have a situation when that waveform pretty much reaches right down to the 0 here, then we have a full scale of modulation, which would be 100% modulation. Now, if we see some dead space right here between those bumps, that means we are trying to modulate it with more than we can. So we are overdriving it. We're pushing it too far. And if we push that too far, it's not going to give us anything. So if we're over-modulating the carrier, you're going to see a dead space between those bumps. So you want to have it as much as you possibly can to going down to 0, but not splitting the envelope, because this here, that is called envelope. And what we did is I showed you what's the percentage of the modulation? Well, you either calculate this distance right here or measure this distance here and measure this distance here, and divide one into another, and you get the ratio. Of course, divide the smaller one by the bigger one, and you're going to get a ratio that's less than 1, of course, because 1 would be 100% modulation, or 0, 0, 1 would be close to that one being 0, then you will get 100%. And this here is kind of like a little bit more complex visual representation of what we did yesterday in the lab. If you look at this here and these A's and B's here, it's just as if you had to program that thing into some sort of a software, or coding. If you had to code it into some software, then you would use that sort of explanation. But yesterday we were able to accomplish what we needed just by, and actually what you did is this that's what we did in our minds, or on paper, in order to accomplish the percentage of modulation. The example we're going to take care of later on, when we have the in-person class, and you actually had to do that during that lab yesterday, so this is not going to be something new to you, but we're going to take care of it as a refresher, just to retain the knowledge as much as we possibly can. Now, amplitude modulation, mixing and intermode. Well, there are some aspects we need to understand. Mixing of the intelligence signal with carrier results in additional frequencies being generated, and that's within the first couple minutes what I was showing you, right? Over class here. So okay, again, mixing of the intelligence signal with carrier results in additional frequencies being generated. Mixers are used in both transmitters and receivers for modulation and demodulation. Well, yes, we need to demodulate the modulated signal so we can understand what it carries. the mixing that occurs when we generate modulated carrier is considered to be desirable. Yes, that's what we want to accomplish. The mixing things with the noise is undesirable, but the mixing with the intelligence, yes, it's desirable. Okay. However, excuse me, under certain conditions, undesirable mixing can occur. And it's not just the noise or the just noise floor. Again, under certain conditions, undesirable mixing can occur, resulting in intermodulation distortion, or also known as intermod. This unwanted intermod may occur at frequencies that are outside of a licensed spectrum or their harmonics, or they can occur at frequencies that will create problems with the intelligence signal processing. As an example, there was a time a few years ago, about 20 years ago, that all of the wireless stage microphones had to be retuned because the frequencies that those microphones were using were okay up to some point. But when the electromagnetic spectrum in the air became more and more a commodity. Why? Well, before we didn't have so many cell phones. Everybody has a cell phone now. Can you imagine the effect on the frequency spectrum that is needed? Before, it was not existing. Nobody had a cell phone. Well, mostly nobody had a cell phone. So the spectrum was able to breathe. Now we're packing things, just like, the road everybody has more cars, the roads become more congested. So some of the frequencies that had to be used for cell phone communication were all of a sudden close to the microphones that being used on the stage, the wireless microphones. Yes, the stage microphones were first, and then the cellular communication came second, but the cellular communication was more important than the microphones on the stage. So the wireless microphones had to be retuned to get away from the frequencies that the transmitters were using. The transmission towers for cellular communications were used. They still have that issue, especially at yes, they do, because yeah, Brandon, thank you. Yeah, because there's so much, and sometimes it's impossible to eliminate all possibilities of any kind of intermodulation distortion, which is interference. The intermod is different from just noise interference, is that the intermod is actually created and it carries something. So, all this, not just the cellular communications, all the Wi-Fi, it uses frequencies. Cell phones use frequencies. Any kind of thing that connects to Bluetooth, it all has to be allocated somewhere, and things, we only have so much space and we have to congest that, so sometimes we're going to have problems. Right? So intermod can cause serious problems for both products and system designers, and finding the sources can sometimes be difficult, and the solutions might be extremely difficult to implement. Yeah, those wireless microphones had to be retuned 20 years ago, And yeah, because if they were not, you would be talking at some sort of a convention or public gathering or whatnot, and all of a sudden the digital communication would kick in, and that would just make everybody turn inside out. You have to angle the antennas to reduce the interference. Is there a reason they might work? Like 90 degrees angle? Well, okay. So there are different types of antennas, and if you angle the antenna a certain way, you're going to have the electromagnetic waves have a certain strength at a certain angle. So if you have the receiving antenna at the same angle, then you're going to get the most out of that transmission. Now, if you have one of the antennas standing up and laying down, then you still might be able to receive the signal, but it's not going to be as much that the receiver antenna is going to receive, because the waves are being kind of shot out of the other antenna at different angle. At certain points, it shouldn't matter that much. However, it does. So if whatever the interference is causing, you can angle the antenna to minimize the antenna being affected by the interfering signal, then you might, but sometimes it's possible, and sometimes it's, the the electromagnetic portion of that is quite interesting, I would say, when it comes to that kind of stuff. It takes some understanding of things, and it takes a while to do that. But how is it that you can accomplish that? Well, it's just like two things. The how do you distinguish what's good or what's bad? Great philosophical question. Well, there's no formula for that, but if you dwell on the idea, you think more and more about it all the time or as much as possible, then it's going to be, after a while, it's going to become obviously clear to you what's good and what's bad. Same as the topographical maps. If you look at those, you just see a bunch of lines and those levels and some numbers, and it just doesn't make sense. But if you just stare at that topographical map and stare without thinking even, just stare long enough, all of a sudden you're going to start seeing that thing in 3D. It's one of those things. So the same thing with electromagnetic waves. So turning things 90 degrees, yeah, but why? Well, that's why, because when the antenna is shooting some signal under a certain angle, and if you adjust the antenna for the most efficient receivage of that signal, then yes, of course, the antenna is going to be affected the most. And if you turn this around a little bit, it's going to be not affected as much, which sometimes we want to accomplish one way or the other. Sometimes you want to receive certain signals, and sometimes you want to reject certain signals. So yeah. Now, the bandwidth. The bandwidth required for modulated signal is greater than the carrier intelligence or intelligence signal alone. Well, there's a Hartley's law, Shannon-Hartley's law. We'll come back to that. It has something to do with how much bandwidth do we need to transmit the intelligence comfortably and at the same time ignore the noise comfortably. So it's give and take kind of a thing. Modulation creates a broadband signal, in contrast to baseband. Remember, we had the whole lesson on what's broadband and what's baseband. I would, if you're still not comfortable with that, I would encourage you to refer to that previous video that is in. It's actually in our playlist, but it's not published. So you have to go and get the link from our class portal. Modulation creates broadband Yeah, that's what we want to accomplish when it comes to broadcasting. Hey, look at that. Broadband has to do something with broadcasting. All right. Modulation creates a broadband signal in contrast to the baseband signal, which means that's why there's the question, why do we need to modulate? So we could create, we could be in control. We could be in control of creating channels, and we could be in control of placing the channels within the spectrum that we do have to use. And since the air is able to carry a lot, the air has a huge bandwidth. It's still a medium, just like the wire, but it's different. It just blanket covers all of us and everything. So modulation creates a broadband signal, which means all channels, everything is present in the medium at the same time. In contrast to baseband, which is a time-sharing concept. Excuse me. Talking too much. Oh, is everybody awake now? So baseband is time-sharing. Go refer to the, I'm not going to explain that again. Not now, actually. Here. Amplitude modulation and frequency domain. When combining any two sine waves through a mixer, we generate a product that results. Excuse me. There you go. I forgot I had that button here. So I could mute things. Well, we already talked about that in the beginning. What do we have? We have the desired output in green. We have the carrier frequency, we have the carrier minus intelligence, we have the carrier plus intelligence, and that's what we see in our FFT screen. Is that all there is? No, there's more. You see there's a little kind of a squiggly thingy there. That means that this is far that way, because we don't see it. There is that intelligence signal and its harmonics, and the carrier and its harmonics. So that's why when that's why when excuse me, that's why when transmitting the signal, it is important to keep to only the stuff that we want to transmit. If we are doing some sort of a lab experiment on a breadboard or whatnot, we create some other things and they're present, but who cares? It's actually good because we can analyze them and see them and all that stuff. But just remember, the airspace is expensive. We don't want to transmit more than we have to. We can't. We're prohibited from transmitting more than we have to. And if we do, we could actually get in legal trouble. That's how important that is. Good thing it's almost Friday. Mathematical models of AM modulation. Well, I'm going to make this one really short. Here is the sine wave equation for carrier. Here's the sine wave equation for the intelligence signal. They're pretty much similar, except for the peak values here. And if we throw them in the jar and shake the jar, that's what's going to come out. Right? All right. I told you it was going to be a short slide. Components of amplifier modulating signal. The expression can be further expanded. Well, that's what's going to come out. That here is considering the upper sideband and the lower sideband. Here's the upper sideband because it includes the angular velocity of the carrier and the intelligence plus the intelligence, and it contains, well, the angular velocity of the carrier minus the intelligence. And here's the carrier. So here's upper sideband, here's a lower sideband. And that's what we would get. We can see that we have a carrier and two sidebands that are plus and minus of the modulating signal. If the carrier was 500 kilohertz and the modulating signal was 3 kilohertz, we would get sidebands at 497 and 503. This is the carrier minus the intelligence frequency, carrier plus the intelligence frequency. Now, just keep in mind that the purpose of the AM module, any kind of transmission, the purpose is not so we could send out a carrier and over that carrier we're going to send a 1 kilohertz sine wave. That's not the purpose of the whole transmission. The purpose is so we can carry some information that we can use, like spoken word, like music. So on FFT, this is what we would see if we had a sine wave, kilohertz. But my voice, for example, it consists of many frequencies and their harmonics and whatnot. So, and music as well. So you're not going to see a spike on left and right, on the lower side. You're going to see a dispersed, almost like rectangular type of. You're going to see some hairy mess on left of the carrier. You're going to see some hairy mess looking thing at the right side of the carrier. Amplitude modulated sine wave, so it's a sine wave and time frequency domains. We have a carrier. It looks like this. Is almost like a 3D over 2D version of it. And we have the upper sideband and the lower sideband, and this is that's what the envelope looks like. We want to accomplish pretty much all the broadcasters with their equipment. For the most part, they're trying to accomplish anywhere the index of the modulation index. In a percentage, and they try to stay within 90 to 95%. We want to have some sort of headroom, so if there is any kind of a transient anything happens, we still want to have some headroom, so we don't overmodulate the signal, because that's bad for the equipment. But if we undermodulate, if we have a little bit more modules, we are going to end up with a weak signal, the intelligence signal. It's going to sound quieter, and it's just annoying. So the modulation we want, and this is a good visual here, We don't want any clipping here, of course, and we don't want any clipping here. So we want to have anywhere between 90 and 95 to stay that way, and we're fine. So this here, looks like it's almost 100% modulated. And if we're splitting the envelope, which means we're going to have too much dead space, like straight line there, that will be over-modulating, remember? We talked about that already. Now, so far we have considered a single frequency sine wave with a constant frequency. That's what we were just talking about. And the amplitude of the modular signal. So it's constant frequency and constant modulation, amplitude. So we end up with a spike here and a spike here. Everybody happy, right? Now, a voice signal is much more complex and contains frequency components from approximately 200 Hz to 3 kHz. And it's constantly changing in frequency, content, and amplitude. It's hard to catch by a human eye what's happening there, but the ear likes it better. So instead of a spike, you're going to have an area. Remember, it's going to have like a hairy mess area here and a hairy mess area here. And to a trained eye, you'll be able to pick that up, because you'll see that little bit of, things are happening here and things are happening here. So these are the side, this is lower sideband, here's the upper sideband. Yeah, okay. You can impress some people by knowing that. If we use a carrier of 1 megahertz and modulated signal of 02.3 kilohertz, we get sidebands below. Now, here's something to understand. When we are going to transmit the carrier, and we're going to modulate that carrier with certain content, could it be music? Could it be voice? Could it be a digital transmission? It is going to create two sidebands, and depending on the frequencies, and those sidebands are going to be, the width or the bandwidth of those sidebands is going to depend on two things: the frequencies of the intelligent signal present in the intelligent signal, and the ability of the equipment to carry them, or the settings of the equipment, which means I'm talking about filtering. And we want to have certain ways. So when we have the upper and lower sidebands, and those contain the same information. So we can cut one of them, upper sideband or lower sideband, and you could have more channels, because in order for the channels to not interfere, they had to be separated by a certain distance to have some breathing space. To not intermod into each other, not to interfere with each other. And if you're transmitting a full carrier, you get pretty good power of the, because you get power, you get to use the power that is contained with both sidebands. And you get a little bit more quality of a signal, because you can spread the intelligence over the two sidebands. But if it's just voice, you can cut one of them off and fit more. So certain bands, and I'm not talking about music bands, I'm talking about certain frequency bands over the spectrum, especially within the amateur radio spectrum. Certain bands implement a full carrier, and two sidebands, full carrier double sideband. Remember that acronym? That one? Yeah, that's how you pronounce it. Some bands will implement transmitting on upper sideband to fit more channels or more conversations within that. And some bands will implement only lower sideband. And I think that radio station is still there. The amateur station in Netherlands, there is a receiver. You can log in, and I'll show you that. It's a pretty cool thing because you can actually control that radio and you can listen to things, and you can switch between your receiving tuner to full carrier double sideband, or you can switch the receiving to either upper side and lower side. And it's interesting because if somebody is transmitting on the upper side and you have your tuner tuned to listening to lower side, you will hear just a little bit, but it's almost distorted. It's almost not there. But so okay, I wonder if he's transmitting on the upper sideband. Switch it, or boom, it just the whole thing becomes alive. So I'll actually demonstrate that to you when we are in person next. I think it's next Monday, because we have a pretty nice screen there, and we can just play with that for maybe, I don't know, a couple minutes, and then you can do it at home once I show it to you. The modulating signal does not have to be voice, it could be a data stream. Okay, let's see what we have here. If the modulating carrier signal is, then we get two sidebands as per below, the upper signal sideband and the lower signal sideband. But then, depending on the information that's there, those are going to be wide enough, and the channels have to be spread far apart from each other so those don't overlap. The modulating signal does not have to be voice, it could be a data stream. And yes, in that receiving station that I'm going to show you, you can actually tune to some of that data stream, and it sounds like some kind of a radioactive water stream. For various frequencies bands used, there are specifications on the bandwidth that might be used that are set by Industry Canada and must be adhered to by product manufacturers. If you don't follow the rules, you can get into a big trouble. Actually, big trouble, including jail, I think, but I'm not a lawyer, so don't quote me. Yeah, so if you transmit the wrong thing, they catch you, and they throw you in jail. Yeah, so be careful with your breadboards. In the image above, the sidebands are shown as rectangular. That would really look like on the spectrum analyzer if someone was speaking, because the voice contains many different frequencies at a certain level. Example, I'm not gonna do that. That we might take care of that on in our in-person class. Effective modulation. Okay. If the modulating index is lower than 50%, the power in the sidebands is 1/4 squared or 1/16 of the power of the carrier. Remember the logarithmic scale, dBs and all that. Since the sidebands carry all the information, because the information that we care about is not in the carrier. The strength of the carrier is just the strength of the carrier that can travel further, and the tuner can easier tune into. And that's it. But the information that we care about is actually in the intelligence signal. So, in the modulation, okay, the power, since the sidebands carry all the information, a lower modulation index is not desirable. Most of the transmitters try to keep the maximum modulation in the 90 to 95% range for best performance, keeping in mind that we do not want to get to 100% or higher. Why? Because we need to have some sort of headroom for some transients. We need some breathing space. And higher modulation, over modulating, we were able to demonstrate that it results in a distorted signal, lost information. A useful relationship for calculating power of the total current as it follows based on the power of the current of the carrier. You get a couple of formulas. We'll play with those. Why do we need power? Well, we need power. Why do we need to know the current? Because current tells us the power. Those two are related. Take care of the example later on. More example, can take care of the suppressed carrier sideband, AM. AM broadcast radio uses double side full carrier. AM, mainly due to the simplicity of the circuitry. For legacy reasons, okay. Because it's been there for a long time. Since all the information transmitted in the sideband is in the sidebands, it is possible to suppress the carrier and even eliminate one of the sidebands. So the carrier can be suppressed, not as strong. You can eliminate one of the sidebands, that's what I was talking about before. And you can transmit in a single-sided AM. Now, again, as I was saying, you can decide whether you want to transmit upper sideband or you want to transmit lower sideband. But then the receiver has to know how to tune it. If you're transmitting upper sideband, the receiver has to tune to the upper sideband and receive things. And same thing with the lower sideband. Single sideband requires more complex circuitry, yes. However, it is more power efficient, and it uses less spectrum. It is used by amateur radio and military. I think it's the last slide here. In order to improve the frequency response, because AM frequency response is not as perfect as it could be. It was designed for voice, and by the way, you can transmit music as well. So additional sidebands. So there's a there are some high definition radio AM stations, but for that you need high definition AM radio tuner to be able to do that, and that results in some widening bandwidth for those two upper and lower sidebands, which can carry more information, which can carry more spectrum, which can carry more frequency response. And when you tune to that, that AM station becomes quite nice and clear to listen, actually. There are some stations. I'm going to try to find out if there is some in our area. There are some in our area to listen to. It's possible. Otherwise, you just use the FM modulation because it has way better spectrum. And here's some questions. I'm going to let you dwell on those. And we're going to take care of them first thing that we meet each other in our in-person class next week. So, today is Thursday, and it's the almost Friday day. So, I wish you a happy weekend, and I'll see you when I see you. Thank you so much.